Morning everybody and welcome to lab 2. Let me explain you the task for this week. So this week we are going to do some arithmetic operations. The first one is add. Okay, add, it can be done in this is the syntax for add. It will be add and then the operand. Now operands will be two because you need to add two things, right? So it could be a register and a memory. It could be memory or a register, memory, immediate. Immediate means whenever you are giving an directly you are giving an data to be added either to the memory, or you can give a data which can be directly added to the register. Since this has not been covered extensively in the theory class, we will restrict ourselves to register adding and register immediate adding, which I will explain you. Okay, so the first example is add AL BL. Okay, so this is the syntax. What it does is it adds the contents of AL and BL, whatever is the contents in these two registers, and finally stores the data in AL. So this is AL. The first operand is the destination register. So whatever is the final sum, it will be stored in AL. So the contents in BL will not be appended. Okay, so BL will continue to hold whatever data it was holding before the add operation. Whereas for AL, whatever data was there earlier, AL, that will be overwritten with the result what we get, and the result is in this case is the sum. So this is true for most of the arithmetic operations. The result will be stored in the source in the destination register, which will get appended, and the data which is in case if that data needs to be preserved, you require it for some other operation, then you need to store that in some other register. Otherwise you will lose out that data which is there, and it will get updated with the new data. Okay, so this is the syntax for that. The second operation, exercise what we will do is add immediate. It means that the format is like this: add AL, okay, -5. So -5 is the hexadecimal number which will directly get added to AL, and the net result will be the sum will be stored in AL register. So here it is why we call it immediate is, which is not, we are not calling this data -5 from some other register or something. So it is directly done here. Okay, so it is we are giving the data itself directly, so that is why it is known as immediate. So also what we need to do is we need to check the status of the various registers after this operation is done. Okay, so if it's a 2's complement number, if you are adding it, if it's a negative number, accordingly we'll have to see the sign bit. Okay, so what are the registers which we need to use, and what are the numbers which we need to do? These things will be specified to you in the problem statement, which I will give you towards the end of this class. Okay, so this is what this is showing an example of 8-bit addition. Similarly, you could have a 16-bit also. So this is so once you do that, you need to this will be the kind of program which you would write, because whatever data is given to you to add two hexadecimal numbers, first you need to load them into the respective registers. What are the registers to be used? That also will be defined in the problem statement. So these are the two registers into which these data are. This is the first two commands is only loading the data required numbers into AL and BL, and then you are adding AL and BL, and you will find the net result in the sum. So this, last time I have explained you how to check the status of various flags, how to check after the operation. You can do step by step, or once you complete the run, you will find the required sum should be available in AL, whereas BL should hold the same data which you have had. So you got to verify whatever theory we have learned. Is this the emulator functioning as per what we have learned, or is there any discrepancy? Then you need to discuss it out and try to understand where is the problem, right? So, and also you need to verify various flags. So this is the this thing you have to do. Okay, so carry flag, zero flag, right? So these things you need to verify. Now there is the second part of it will be 16-bit number addition also. Okay, a word addition. The only difference here is okay, you will move it 16-bit data into the registers. Like in this case, in this example, in CX we are moving a 16-bit data, in DX we are moving an 16-bit data, and then we are adding CX and DX. So obviously the sum will be again an 16-bit, and probably there could be an carry depending on the numbers that will get. So the carry flag will be accordingly activated in case there is a carry, and the net result will be available in CX. So this is 16-bit addition. It is very similar to 6-bit. Now if you see, there is no register, separate register in which the carry, if it is more than 16, the result is more than 16, there is no separate register in wherein that one will be stored. It will be only there in the carry flag. Okay, and the carry flag will get updated with the next arithmetic operation. So in case you need to store that carry, and you have to remember that there was a carry in this operation, then accordingly you might have to store that value one somewhere, or you have to make necessary storing in your code. You will have to take care of those issues. Okay, so now similarly you have an the second one is subtraction. The syntax is sub, again sub. It is very similar to add, register, memory, memory, register. You can do register subtraction, you could do. You can also do memory immediate and register immediate. Okay, and this is the syntax sub AL BL and sub AL. It will do in 2's complement method. Okay, whatever is the subtraction. So these are the flags which will get reset after as soon as you complete your arithmetic operation, which is subtraction in this case. And also these are the carry flag, zero flag, sign flag. If it's a negative answer, this will be 1. This is overflow in case 2's complement. If the answer there is an overflow, then this we have learnt in our digital class. What is an overflow in 2's complement? That is, if the net result is out of the range, then this becomes go. This is even and odd parity, and this is the auxiliary carry. Auxiliary carry also we discussed in the last class. If there is a carry from the from the 4th bit to the 5th bit, like if S0, S1, S2, S3, these are the first 4 bits, then from S3 to S4, if there is a carry, then this will be set to high. And the use of this is whenever we are doing a BCD addition, we know that if there is a carry, we need to add 6. So generally this flag is used in case of BCD addition. Normally we don't use that. Okay, then we can also do 2 subtraction. This is again the code which we write. We are going to first load these registers, lower AL and BL with specific values which will be given in the problem statement, and then you do the subtraction, and then you check the flags and also the values of the AL and BL. Here also, like in the case of addition or in the case of all arithmetic operations, okay, this will be known as the source, and this will be known as the destination. So after the syntax, it is the destination register, and the destination register, the final result will be stored. So the data in the finally, once the program is complete, the destination register will have the final result. It will not have the previous result, whereas the source register will continue to hold whatever data it is there before the arithmetic operation. So this you need to take care of that, and you need to you can run this program, and then you can see what are the various flags. Okay, so the third operation which you are going to do is multiplication. Now in the multiplication, in the syntax, if you see, it is multiplication, and in the operand you will see there is only one. It is either the register or memory, because it is understood that one of the operand will be AL. Okay, or it could be AX in case we are doing a 16-bit. For an 8-bit, it is understood that it is AL. One is AL, and the final answer, and also the final answer cannot be only AL, because you are multiplying AL, say with BL, right? The answer now, they are 2-bit multiplication, so the answer has to be 16-bit. So the final answer will be in AX. Right, so that is how the syntax goes. Similarly, for a 16-bit operation, multiplication operation. It only you need to specify only the memory or the register, so that will be the only operator. You will write multiply BL or whatever. So the other thing which is going to get multiplied is AX, which is understood. It is implied. Okay, it has to be AX. Okay, and since the answer it is going to be a 32-bit, we require a 32-bit register. So since we don't have a 32-bit register, it will be stored in DX and AX. Okay, so these two together will 16-bit registers will form a 32-bit register, and DX will be the MSB 16 bits, and this will be the LSB 16 bits. Okay, this will be the higher order 16 bits and the lower order 16 bits, and accordingly the flags also will get set. Okay, so this is the example code which is given. So we are first we need to load two figures will be given, whatever is to be multiplied. One you got to load it in AX, the other in BX, and then you write just multiply BX. So once you write multiply BX, it is understood it is going to multiply with AX, and the answer will be in DX and AX. So that you need to verify after your program. You'll also have to check the carry flags and other flags. Okay, so this is multiplication of 2 bits. In multiplication of 16 bits, so you are initially loading a 16-bit data into the AX register, and then you are also putting a 16-bit in BX, and then you are writing multiply BX. So it will multiply these two numbers, and the answers will be stored in DX and AX together, right? The content in both AX and DX registers. So you need to verify whatever answers you have got. Okay, and the last one is division. Division is very similar to multiplication. Again, you write division AMX, so it will be AX is implied. Okay, so you are going to divide AX by DX, whatever is there. Okay, so in that case by the remainder will be available in DX, and and the quotient will be available in AX after doing the division operation, right? So if you see this command AX, okay, you are and BX you have done, and you are doing an division out here, right? So you will find the remainder will be in DX, and the quotient will be available in AX. So you need to, it will be in AL and DL, sorry, because once you are dividing, these will be only 8-bit information available, right? So so these will be AL and DL. The information whatever after division will be available in AL and AL. So it is expected that 16, and when you divide this by, the answer will be in AL and 16, because they are 8-bit information available which is available. So you need to do this also. This is for again division of the similar one, dividing for 16. So check the contents in AX and DX registers. Okay, after the division. So quotient and remainder, you go to check both of this. So this is the task for the next week which is given. So you need to add these two numbers. So in the sample programs which I explained you, I used AX and AL, BL, those kind of registers. Here the registers have been specified. This is just, you can use any register for that matter, but just for the sake of testing your knowledge, these registers have been specified here. So you need to use these specific registers. You need to load the data in these specific registers and do the check. So after having done this, save all the files, and next week I will evaluate the results and your simulation. So that's all for this week. Thanks a lot.